Now sometimes I need to decide whether something is a stream of particles or a wave. We had the same problem in the last chapter when we were looking at the cathode ray. We wanted to know what the cathode ray was made out of. Is it a beam of light that is a wave phenomena, or is it a stream of particles? And we came down on the second one in chapter 2. Now in this video I'm going to show you some slightly more sophisticated ways to decide if something's behaving like a wave or behaving like a particle, because that's going to be kind of essential to the whole idea of quantum mechanics that we're going to go into in this chapter. Now let's look at a couple of particles. Maybe I've got a couple of electrons, maybe I have a couple of baseballs, whatever you want, and I'm trying to get them to collide. I'm trying to get them to move into the same region of space. They won't do it. Particles collide. And they don't occupy the same space, but when they collide, they're going to do it at a precisely located spot. So you can know exactly where they collide. They're going to hit each other and bounce off of each other. That's a particle behavior, collisions. Something completely different happens when you have a couple of waves move into the same region of space. Say I've got a wave coming here from the left. And say I have a pretty similar wave coming in from the right. So there's a red wave and a blue wave coming in there. Now, let's define a word before I start talking about this. Here's where the baseline for the two waves would be. This is where you'd be if you didn't have an up or down tug making the wave. The height above the baseline, so this is my red wave. This height here is called the amplitude. The amplitude of the wave. And it's a tug. It tugs whatever is riding on the wave away from where it would have been if the wave wasn't there, up here. Now if I look at the amplitudes of these two waves, they're the same. And what will happen when they move into the same region of space is that they will no longer act like separate waves. They will kind of melt together. And what will happen is their amplitudes will add up. So the red wave's amplitude is there at this point, and the blue wave's amplitude is here. And if I add this to this, I'm going to get a resultant wave with an amplitude up there. And if I go for all the points along where they're moving into the same region of space, I'm going to see that what I get is a resultant wave that looks like this. So when you have a couple of waves, they move into the same region of space. They can do that, and they interfere. That's what this is called, interference. They don't collide, they interfere. That is that when I say interfere, that means that their amplitudes, their peak heights, add up. So you're adding the two amplitudes together to get a total amplitude. And here, because the amplitudes are pulling the same direction, they're making each other stronger. The resultant wave is stronger than the waves that you started out with. This is called constructive because they're building up each other. You get a bigger amplitude. The resultant wave has got a bigger peak height than the two waves that went in. So this is a pretty important difference between particles and waves. Waves interfere, but particles collide. Now, there's another way that they can interfere. Suppose you've got a red wave and a blue wave that look like this. Here's the red wave coming in from the left into a region of space, and here's the blue wave coming in from the right. Now they're kind of out of sync with each other. And what's going to happen here? Here's where the baseline would be. Blue wave is tugging down, and red wave is tugging up. So they're going to cancel each other out. Here in this case, both of these waves have the same amplitude. So their amplitudes are equal and opposite, and they're going to just really kill each other off. The resultant wave is going to be pretty close to what the baseline is. The resultant wave would look like that. And in this is a case of destructive interference. The resultant wave has smaller amplitude. Now this is how noise-canceling headphones work. So you have background noise outside your headphones, and what the headphones will actually do is rebroadcast the sounds from outside slightly out of sync. So you're hearing both sounds. Here's the outside sounds, the blue wave, and then here's the rebroadcast outside sounds from your headphones, the red wave. They will cancel each other out, and you won't hear the outside sounds this way. It will kind of deaden them through destructive interference. So you can have destructive and constructive interference here. All right. Another thing that particles do that waves don't is that particles move pretty much in a straight line. Unless you add an outside force to them, they go the way that they go. So suppose you've got a slit here. Here I got a wall, and it's got a gap in it. And I start firing electrons, or let's not do electrons. Let's say I start firing something heavy through here, bullets or something. Bullets are going to go straight through, and they're going to strike the screen out there. And you'll just see them pile up in that one spot there. They'll move in straight lines unless you add some kind of outside force to them. If you have another beam that's firing, at right angles here, they'll hit each other, they'll collide, and they can scatter around a little bit. That would be an example of adding an outside force here. But you'll get a pileup of particles there. Not so with waves. Here's that slit again. Now, here I'm going to have a wave. Now imagine these are like water waves, and this line that I'm drawing is the top of a peak of water. So if you were looking at this, from a side view, let me do like a side view here. It'd look like this. So you've got this wave coming in, and then it hits this little gap in the wall. And you've got a screen or something over here, and you want to see what's going to happen. Now, it's not going to move straight through like the particles did. It's going to instead bend around the edges of the obstacle here a little bit. And it'll fan out from the little slit. This is called diffraction. And that's a a word that can mean a lot of different things. It means basically bend around small objects. I would say when the obstacle is smaller than the distance between the peaks here, it can do this kind of thing. So if this is wide enough, it can shine straight through. But if this is narrow, if it is smaller than, your wavelength is what it's called, the peak to peak distance, then you can get something like this happening. Now this is how your camera works. This is the average, or this is the aperture of the camera. It's like a little tiny pinhole, and the light can fan out, the light being a wave, can fan out from the pinhole and expose the sensor in the back of the camera. So this is how cameras work. By changing the size of the aperture, you can change the amount of light that you're letting in, and how much light is going to be hitting the screen through here. This is another big difference between particles. Particles will move in straight lines, and waves will diffract. Now sometimes there's a phenomena that particles do that we can name. Here we got particles up again. Imagine that these are gas molecules, and they are all on this side of a wall. Maybe there's a container here, like a balloon, and it's got a little hole in the side. Well, these gas molecules are constantly pummeling the sides of the balloon, and they're going to hit this hole and go through, and you'll get a beam of gas atoms coming out here. When that's happening, this phenomena that we're looking at here is called diffusion. You can say that the particles effuse, in that situation. Whereas the waves diffract. Now there's a pretty famous experiment that you can do that shows whether you got waves coming in to a slit or particles coming in. And this is one quick way to do it. But when you have two slits, you can really clearly see that you've got a wave. Imagine that I've got two slits in a wall. And I have a bunch of gas molecules over here, and they're constantly colliding with each other and with the walls of the container. And when they happen to hit one of these holes straight on, they can go straight through. And if you have a screen or something over here, you can detect them. You can see that they're all piling up there and there. So you see an image of the two slits there with particles. But when you have waves, something completely different happens. Here's the screen. Here are the two slits. Now I'm going to have some waves. And again, I'm going to draw the tops, the peaks of the wave here, coming in. And what it's going to do is diffract around the edges for the top slit. And it's going to do the same thing. Let's see if I can draw it. Okay. It's going to do the same thing here. Now you're going to notice something kind of interesting happens. When a peak hits a peak, that is when one of these lines hits another line, you're going to have constructive interference. It'll be a bright spot. It'll look brighter because the wave is higher there. And if you take a look at how this is working, you're going to get a bright spot. If you follow this line here, you're going to get a bright spot on the screen here when all these things go and hit the screen. You're going to have some other places where that intersection happens as well. And what you're going to see is an alternating pattern like this of bright spots. And where the troughs hit the troughs, so halfway between these peaks there's a trough. Let me draw that as a dark dotted line. There's the trough for this wave that's diffracting out of that slit. And here's a trough for this wave that is diffracting out of this slit. Where a trough hits a trough, you're going to have a dark spot. Or where a peak hits a trough, you're going to have a dark spot. Because you'll have destructive interference there. So if I come down here to that point, I'm losing my marker there. Here's the trough, this dotted line, and here it's hitting a peak. There's a peak hitting a trough there, so I'm going to get a dark spot. And if I follow those dark spots down here, there'll be a dark spot between each of these light spots. So you will get an alternating light and dark pattern on the screen here that is pretty striking. And this is called an interference pattern. This is a pretty famous experiment. It was done by Thomas Young in the early 1800s, and it was proof that light acted like a wave because you saw this interference pattern, light, dark, light, dark, light, dark on the screen behind a double slit. And you can explain it in terms of diffraction and constructive and destructive interference. Only waves do this. Because only waves can interfere and only waves can diffract, only waves can produce an interference pattern. And this is the number one experimental way to prove whether or not you have a wave or a particle. Now, one more big difference between waves and particles is that if you look at a particle, it's a tiny little thing like a bead or something. So there's the particle. It has a precise location. You can tell where it is. And it also has a velocity that you could measure. You can measure its speed, no problem. Now with a wave, the wave may also have a velocity. You can measure the velocity as the speed that a peak is moving to the right here or to the left, whichever way it's moving. So a wave also has a speed. And what about a precise location? I don't know. I don't think you can say you have a precise location because the wave is made up of a lot of peaks and troughs that are spread out through space. So the wave, we say, is delocalized. That is, it's not found at one point in space. Whereas a particle is localized. You can tell where it is. This is the third big difference between waves and particles. So what are the differences? Waves can diffract, bend around small obstacles. Particles can't do that. When waves move into the same region of space, they interfere with each other. They can interfere constructively or destructively. When particles move into the same region of space, they collide. That's a big difference. And then finally, if you look at where these things are, a particle can have a precise location, but a wave is really spread out through space. It's delocalized. So these are the differences between these two things.